by Professor Hosur, and this will be like on NMR spectroscopy and its application in the structural biology. So if you think like our best field gaps of structural biology by NMR spectroscopy. Whatever is not amenable by many other techniques, how you can access those by NMR spectroscopy. So many of you who will be who is not familiar to Professor Hosur, so he is currently distinguished visiting professor in our department, and going back, he started his academic career from IIT Bombay. So he did his master's in chemistry from IIT Bombay in 1979, 81 probably, and then he did PhD from TIFR with Professor Girish Kovic, who was one of the pioneers in NMR spectroscopy. Then for postdoc, he went to ETH Zurich, worked with Nobel laureate Professor Prof, came back and started biomolecular NMR in India. So he is the pioneer in biomolecular NMR in India, and all the work in biomolecular NMR you see has originated from Professor Hosur and also from Professor Chari, who fortunately studied. These were two strong pillars of biomolecular NMR in India, and we all originated from that. So I'm also my whole training started with Professor Hosur as a PhD student in TIFR. So I also switched from chemistry to biology, and because of him, I am here doing biomolecular NMR. So after TIFR, he was director of Center for Basic Sciences, and then he is currently distinguished visiting professor. And of course, wants to establish a field in a country, the other things will follow. I don't want to name also. So I don't want to stand between you and him. I'll just be one of you. And I also
I can add one line.
Yeah, you can.
So I was visiting ETH Zurich in 2013-14. So I was meeting Richard Ernst, having a coffee because I took his appointment to have a coffee with him. So he was visiting Professor there that time. So he returned. The first thing he asks, "How is Professor Hosur? You are from Mumbai." So that is Professor Hosur. He's a Nobel laureate. I don't know. He's a very pioneer for the NMR as well as MRI. And Professor Richard Ernst, last time he asks that. So you are from Mumbai. How is Professor Hosur?
Thank you.
He's amazing.
Yeah, so
Okay, so
then we can
thank you for your introductions, and it's a great pleasure for me to be here in IIT Bombay, which is my alumnus. So it's a full circle. So I'm very glad to be talking to all the students here. There are students from biology, there are students from chemistry and chemical engineering, and all of you will realize and recognize as we go along that NMR is such an interdisciplinary subject. We need inputs from physics, chemistry, maths, biology, computers, medicine, whatnot. It is there everywhere. So it's all pervasive. So of course, it's such a huge field, and it is an extremely difficult task to say everything about everything that is happening in NMR. That's not possible. So, however, depending upon the audience, the interest, we can actually filter out information and give that information to excite them to go into that particular area and pursue the research in that particular front. So that is my task today. I will try and give you the fundamental principles of the technique and how it is so exclusive compared to the other techniques. And that's why I gave this title as Converting Sour Grapes into Sweet Grapes by NMR spectroscopy. So let's look at that. And all of you have heard this story of a fox and the grapes. Right? So there is a hungry fox. He's very hungry. He looks here, there are grapes here. He wants to eat those grapes. This is a very common story. Jumps and jumps, falls, takes it back and makes a run and then jumps again, falls back. Finally, he says he's not able to get it. Then, oh, all right. This grapes must be sour anyway. So we'll go away. Now, here is the other fellow who is able to reach there. So this is an NMR spectroscopy. So what are these sour grapes and how one can reach this from NMR spectroscopy. That's the kind of an objective which I have for this talk. Okay. Now, structural biology, in brief, is understanding biological function at molecular level in terms of structure and dynamics. So you have your structural biology in the center, you have the structure and dynamics. Of course, there are other components to it, but these are main primary things which are of importance. And you want to understand all these two features in structural biology. Ultimately, you want to understand the biological function, which is a consequence of these two factors. Now, this is the slide, this part of the slide. Okay. So this is the protein world. Here you have the ribosome. Synthesis happens of the protein chain, which comes here in an unfolded protein to begin with. And of course, you will see many of the so-called intrinsic disorder proteins also belong here. Okay. And then unfolded protein has different fates. It can actually disorder the aggregate, it can fall or get broken up in pieces, or it can go through a certain pathway where there's certain intermediates and make a folded protein, which is called the so-called native protein. Often we think this is the functional protein. And even these proteins will have certain regions which are disordered, and we call those as intrinsically disordered protein regions. Okay, the fully folded proteins also will have certain regions. In fact, it turns out that nearly 40% of the proteins have such kind of disordered regions. And many times, these disordered regions are the ones which are functionally very relevant. And the IDPs do not assume a particular function, but they don't have a structure, but they assume certain structures when they have to do a particular function. That's why they are able to carry out a multitude of functions in a given cell. Now, the fate of the protein is very different depending upon what pathway it goes through. It can break up here, or it can aggregate from here to form certain prefibrillar species, and then, of course, forms amyloid fibrils, and we know all of these are responsible for many diseases. And if you have this final state, of course, you can crystallize it in the crystal structure here, or it can also form a fiber, which is in the case of certain kind of situations. Okay, oligomers can form. So there are various fates for the protein which is synthesized in the ribosome. And then you have this folding funnel, the protein which goes from here to here. This is diagrammatically represented in this manner. This is the so-called native state of the protein, which is energetically stable here. And you have the unfolded regions here, which are on the surface, which are numerous in nature. Millions of conformations are possible here. And each of them follows a particular pathway to reach this final structure, the so-called native state. Incidentally, I must also tell you that this thing is actually a kinetically driven step. So the native state is actually a kinetically driven state. Ultimately, the most stable state is this fibril. Eventually, as Chris Dawson said, that every protein must go into the fibril. That is the thermodynamically most stable state. And this is a kinetically driven state. So temporarily it will form this, but anything that happens disturbs this native state, it will go over to the fibrillar state or some disordered states. So the protein has to pass through a certain kind of a barrier here. This is the energy on this axis. So this is the native state. And then it can go through any of these barriers and it can get stuck anywhere. And if it happens, if it is not able to come out of those areas, then it forms a misfolded state. Misfolded states can lead to different kind of aggregates, then they will lead to diseases. Okay. So how does the protein fold from here to here? Is that understood? This is called as the Levi-Strauss paradox. And it can take astronomical years if it has to, all degrees of freedom have to be scanned in the particular protein chain. But it happens sometimes in microseconds, milliseconds, minutes, hours, things like that. It happens very rapidly. So what are the pathways? Is there any particular way that this can actually go? Or is this something random? So various kinds of theories they evolved, and how do you find out that? Can we find out that? Okay. Then you have this protein-protein interactions, protein-substrate interactions, and the IDPs. Okay. This is the protein world. Okay. Similarly, you can also describe for the RNA world. You can also describe for the DNA world. All kinds of structures are possible in all macromolecules. RNAs are enormous in structures. There are many, many things. Of course, I can't be covering all of the RNA parts. I will cover only the protein parts in this lecture series. Okay. Now, X-ray crystallography has been the most popular technique for determining structures. Okay, starting somewhere in the 1900s. Of course, the X-ray was discovered in 1900s. The first structures came out in somewhere in the 1950s. Insulin was a structure which was the first structure to be solved, and Dorothy Hodgkin got the Nobel Prize for it. There is and then, of course, this area has grown. And what it involves is you have to grow a crystal. You have to grow a crystal of the protein, and then you get a certain kind of a pattern, which is called the diffraction pattern. So the X-ray, so when we pinch X-rays on it in a particular way, and then you get the electron density distribution in the molecule, and with this electron density distribution, you will get the structure of the molecule. This is in brief. Okay. So the structure process involves these particular steps. We have a crystal. First of all, the crystal has to be grown, and then you must find this diffraction pattern, and then you get the electron densities, and then you get the structure. Of course, this has been the most successful method. And how many structures have been solved? Look at the PDB. There is a so-called protein data bank where all the structures which are determined are deposited for use by various other people. Okay, because it has to be used by somebody. So for functionally, for various other things, it's used. So you have seen this started somewhere in the 1970s. There is only some one or two kinds of a thing. And today you have 140, 160,000. How much it is? 180,000. About this here, 170,000 structures deposited into the PDB. So many structures have been determined. Okay. So clearly it's an extremely powerful, extremely useful technique for determination of the three-dimensional structure of the molecule. In recent years, you also have another technique which has come into the fore, and that is cryo-electron microscopy. Cryo-electron microscopy also works with electrons, of course, in that one, and then you can handle much larger systems than you can handle with X-ray crystallography. Huge signals, 500 kilodalton or megadalton, that sort of the size of proteins or protein complexes can be determined, and the technology also has grown so much that you're able to get as high a resolution as this, sometimes even less. So you get 2.9 angstrom resolution structure. Here is the structure, huge structures with certain complexes here, with detergent here, with the lipids here, and the cholesterol here. You have the structures determined of this using cryo-electron microscopy. Therefore, there is a stiff competition between X-ray crystallography and cryo-electron microscopy. Are these exclusive? Of course not. There are some things which you cannot do by cryo-electron microscopy. You do by X-ray crystallography. Okay, and you do at a very low temperature. Cryo-electron, cryo-EM, you work at a very low temperature. Okay, and for the X-ray, you need to have a crystal in the first place. Okay, so these have been extremely powerful techniques. All right. So now, where are the sour grapes? You've got very powerful structures techniques. Where are the sour grapes? In the early days, people did not believe that these structures are useful anyway. So like the Fox saying these are all sour grapes. These structures are not useful. Why? Because these are not in the solution. Inside your cell, everything is solution. So you must have a solution structure. So solution structure was not possible by these techniques. Second, internal dynamics in the proteins. Are the proteins flexible? Are the proteins rigid? If there is a dynamics, can we determine it? No. You cannot determine that either by X-ray crystallography or by cryo-electron microscopy. Many times, those people who use X-ray crystallography studying complexes or for cryo-electron, they actually cut out certain portions of the protein segments to make them crystallize. If you have a flexible domain inside your protein, it will not even crystallize. Or if for some reason you got the crystal, that the loop areas which are flexible, you will not see them. You won't see electron density for proteins. That will be missing. So therefore, those areas cannot be understood by cryo-electron microscopy or by X-ray crystallography. Folding pathways and intermediates, how will you approach them? How does a protein fold? As I said, the native state is a kinetically driven state. So if you have to understand that, you have to understand the pathways. What are the intermediates? If the intermediates are accumulating or if they are misfolding, they are not able to come out of that well and into the native state, they cause diseases. So we must be able to understand these intermediates, and these techniques will not allow you to do that. Okay, intrinsically disordered proteins, we can never study these by either X-ray crystallography or cryo-electron microscopy. Okay, so and these are highly disordered. You cannot get crystals of those ones, and whenever you see electron density in the X-ray, the electron density will be missing in these areas. Mechanism of self-association. How do the proteins self-associate? Why do they associate? Can we understand at the residual level detail? So you need to have a pathway. How does it go? From the monomer to the multimer, how does it go? Can we understand this? This is not possible from those techniques. Then kinetics and mechanisms of interactions. This follows from there. Then insights into metabolic disorders, which are the diseases. If there is a metabolic disorder happening inside your cell, how does it happen? Where does it begin? Which portion of the protein is responsible? Which are the metabolites which are responsible? Can we understand these things? So these are not possible from these techniques. You can list more. So I've listed some of those very popular ones. These are your sour grapes. So as somebody said, solution phase NMR can never be displaced. Solution state NMR is the one which is giving you all of this information. So it will remain forever. It is a greenhouse always. Okay. So therefore, one has to follow this process and try and understand the principles of these techniques to be able to appreciate how one can determine these factors in your living system. Okay. So this is the outline. So that was the introduction. That was a kind of an introduction as the motivation as to what are you talking about? Why are we doing this? So that is the motivation. Now we have to go into the details. So in order to do that, we have to understand the principles. First of all, you have to understand the NMR principles. Then you have to understand how structure determination can be done. One can study dynamics in the proteins. Then what are the steps here? What are the various techniques which are available here? Then finally, I will also show you the results of various approaches in all of these matters. Okay, so this is the way I organized, but I'm open to any suggestions from you people. In case you want a particular kind of an extension in certain area, I can always modify these lectures so we can go on into that. So ultimately, the dissemination has to be good. So the transfer of information has to be useful for all of you. Okay, so this is now back to the basics. So the NMR research front, NMR technique was discovered in 1946 as a basic discovery in the solution state, in the aqueous phase. Before that, it was also done in the gas phase by Rabi, 1944. He won the Nobel Prize for it. Before that, magnetic moment of the nucleus was discovered. That also got the Nobel Prize. And then 46 basic discovery in the solution phase was done by Hosur and Bloch, and they got the Nobel Prize for it in 1952. During this period, this is the boom period, there's so many discoveries happening here, the chemical shift, the coupling constants, or Hosur effect, spin echo. I will touch upon all of these ones. Okay, I will mention these things. You will not go into the theoretical details of those ones, but I will touch upon those ones because you need to use them. You need to use all of those. And then you have the spin decoupling. This, of course, is very exclusive to the solid state NMR. Then Fourier transform NMR is another revolutionary thing, which is revolutionize the use of NMR, how we perform NMR experiment. And then you have two-dimensional NMR, another revolution in NMR, which actually allowed you to go into larger systems from peptides to large proteins, bigger proteins, flexible proteins, whatever. Then you have NMR imaging. This is another parallel field which goes into the MRI technique, which you are not going to touch upon that here. And then you have multidimensional NMR, which is again useful for protein structure determination or any macromolecular structure determination, multidimensional NMR. And in the 1970, dynamic nuclear polarization came into it. This actually was an old idea. This was 1970, nuclear polarization was an old idea. That is, information is transferred from the electron to the nucleus. That is dynamic nuclear polarization. But this was an old idea, but it came into prominence once again in 2008 with biological applications. And that is Bob Griffin in MIT started using it and demonstrated the use of that. And then, of course, in solid-state NMR, this became quite useful. And then you have the current technology development, artificial intelligence and machine learning. This is the current technology development in NMR. Progress is unlimited. Okay, so how much you can do? All of you must have heard about this AlphaFold. This is a software which actually can predict the protein structures very accurately. Okay, so artificial intelligence and machine learning is also coming into the NMR field in a big way. Therefore, there can be another revolution happening in due course of time. And then you see in 1991, the first Nobel Prize in chemistry to Richard Dunst. This is what Samir was telling just now. And it is, he got the Nobel Prize for the discovery of Fourier transform NMR and also two-dimensional NMR and also NMR imaging. Basic principles. Some portion of NMR imaging was given by him. Then this was the Nobel Prize in chemistry. This was the Nobel Prize in physics. There was the nuclear magnetic moment. Okay, and that demonstrated the resonance phenomena, which is actually in the domain of physics. And then came the Nobel Prizes in chemistry, two of them, Ernst and Wittrich. This was in 2002 to Wittrich, and this was for the protein structure determination. And that was the debate when it was that is the is the solid state structure good enough? Is it necessary to have solution state structure? The question which was there before. And he determined the structure of protein in solution. There was a lot of debate at that time whether this structure is good or that structure is good. And finally, it turned out, fortunately, that the solution structures and the solid state structure are identical. And why does it happen? It happens because the crystals also have a lot of water in it. A lot of water molecules. 60 to 70% of the protein crystal is full of water. And that's why the two structures are similar. And therefore, you can use the crystal structures for the purposes as well. Wherever you can determine the solution state structure, you do it. And if you can do it in a solid state, fine, well and good. You can do it there. Then the Nobel Prize in Physiology and Medicine to Paul Lauterbach and Peter Mansfield, they did further development, quite substantial developments, so-called ecoplanar imaging and things like that. And that added to this NMR imaging, which was originally given by Richard Ernst. And so that got the Nobel Prize in now what area? Physiology and medicine. You see, now it's all pervading. Start with physics, then you are in chemistry, then you are in physiology and medicine. More to come. You have to wait. Yes.
Since you are talking about the history, E.M. Purcell also wrote a very classic paper on life at low Reynolds number. So what is the connection of that to the NMR? Are these two things related?
Life at what?
Low Reynolds number. He wrote a very classic paper in 1976.
No, I don't even hear you properly.
See that E.M. Purcell also wrote a very classic paper, Life at Low Reynolds number, which is a very popular paper, highly scientific paper. There is a connection of that to the NMR.
No, probably not. No. So now coming into this first principle, what is this technique? What is this technique? Nuclear magnetic resonance. Every nucleus has a property called as a nuclear spin. It's just like I have a hand, you have a hand, everybody has a hand. It is a property. It is the property of the nucleus, which is called as the nuclear spin. Okay, it is also called as angular momentum. Okay, that is in quantum mechanical terms. We will not go into that one. And this nuclear spin results in the magnetic moment for the particular nucleus. And the nuclear spin is a number which actually can take only discrete values here. It has a 0, half, 1, 3 by 2, and so on. And the magnetic moment is related to this nuclear spin by this constant here, which is called the gyromagnetic ratio. Okay, so and these are discrete numbers. Okay, so magnetic moment therefore has discrete values. Nuclear magnetic moment has discrete values. Now, if you put the nuclear spin in a magnetic field, then it will only have certain orientations possible. This is again a quantum mechanical picture, and that is if you take a spin of half, that is the half value here. Of course, notice that if we have a 0, then it has no magnetic moment. Okay, carbon 12 is I is equal to 0. So it has no magnetic moment. Therefore, carbon 12 is not NMR active. So this has to be non-zero number. If you have a number half, then it has two possible orientations. And those ones are this given in this manner. Nucleus magnetic moment makes a particular angle with respect to the magnetic field. And if you have two possible orientations, one is here, other one is here. And this is determined by the component of this magnetic moment along the z-axis, and that is this here. It can take a value of half h cross. I am not written h cross here. So it is either half h cross or minus half h cross. So we have this number, which is also a quantum number, and we have two possible values there. And those are indicated here in these two orientations. You have an ensemble of magnetic moments, right? Ensemble of spins. All of these spins, there are, how many spins are there? Suppose you are working with 1 millimolar solution. 1 millimolar solution, how many spins are there? How many nuclear magnets are there? So you have 1 molar is 1 Avogadro number, 1 mole is 1 Avogadro number, 10 to the power 23. So 1 millimolar will be 3 orders of magnitude down, 10 to the power 20, that's per liter. If you put 1 mole per liter, but you take 1 ml, another 10 power 3 down, so 10 to the power 17. 10 to the power 17 spins are there. So and they distribute it between these two levels. If I take a simple proton or any particular thing which has a spin of half, then it is what atoms which are spin of half. I will show you that proton, carbon 13, nitrogen 15. These are all spin of half. Okay, and they will be distributed between these two levels. They will be oriented either here or here. That's why I shown so many arrows here. Okay, there are certain numbers here, certain numbers there. Okay, of course there will be more numbers here than here. They will show in the next slide. So in the presence of the magnetic field, the Z component of I will have two possible values, and that is as I said here, half H cross or minus half H cross. That is this orientation. These are called as the alpha and the beta states. Which orientation is called the alpha state? This is called as the beta state. Okay. Now what is okay? These are some of the data for the different nuclei which are of common interest in biology. You have the proton here, the deuterium here. This is the spin of 1. Of course, this is so much the material science. Carbon 13 is spin of half. This is also so much in the material science. We don't do so much in chemistry or biology. This one we use half, half, half. So by and large, mostly we deal with spin half systems. If you're working with biology, work with either proton, carbon 13, nitrogen 15, fluorine 19, P31. So all of these are spin half systems. Mostly we will be concentrating on those ones also. Among these, which is the most sensitive? Most sensitive is the one which has the most highest magnetic moment. Highest magnetic moment is determined by the value of the gamma, right? Because mu is equal to gamma I wrote earlier. If gamma is high, then of course it has the highest value. Therefore, proton is the highest sensitive nucleus. Okay, and here also have the natural abundance here. Proton is almost 100%. Okay, carbon 13 is 1.1%. This is not so naturally abundant. And nitrogen 15, oh, nitrogen 15 is not listed here. Okay, I should put that there. Nitrogen 15 is 0.37%, 0.37%.
Is it 417 that is?
I think, yeah, this is 5 by 2. This is 5 by 2. That's different. So 0.37% is nitrogen 15.
So 19.8 is 100%.
19 is 100%. Yes, and fluorine is also quite a useful thing. In many of these diseases and drugs, fluorine is being used nowadays. Okay, and this is also used mostly for material science there. For phosphorus is 100%, this is half. You see the sensitivity wise, proton is the highest. Okay, then comes this phosphorus, next highest in terms of the gyromagnetic ratio and the magnetic moment. And then comes carbon 13, and nitrogen 15 is later. Of course, fluorine is also very sensitive. Fluorine is also very highly sensitive one. Okay, now what is the principle of NMR? You take a sample which consists of 10 to the power 17 spins, nuclear magnets in your solution, put them in a magnetic field. This is the magnetic field. And these energies, these ones will separate out because of the interaction. The magnetic moment interacts with the magnetic field, and therefore these two different orientations will have different energies. So depending upon the strength of the magnetic field, the energy separation between them will be different. Okay, and that is determined by Boltzmann statistics. Okay, there is always more here than here, and this is determined by Boltzmann statistics. Now, what happens is when you have, if you supply radiation, if you give radiation which is equal in terms of the energy for this compared to this, there will be absorption of energy. That will give you the signal. That is your NMR signal. We'll come back to this a little bit in a few slides more. Okay. So intensity of the line is proportional to the population difference between these two here. Okay. Often it is said this is population difference is extremely small, which is true because the energy separation is very, very small in the radio frequency regime. Radio frequency regime is so much less compared to the optical spectroscopy. Okay, therefore fluorescence is an extremely sensitive technique compared to NMR or even EPR, whereas this one is most useful because of various other kinds of applications. So this is Boltzmann statistic. The difference between these two populations is very, very small. Okay, but that itself is quite useful. Okay. Now what happens? Another thing that happens when you put these spins in a magnetic field is these ones actually precess around this magnetic field, and that is called as the nuclear precession. And these ones are not stable at one place. they will be going around here because of the interaction with the magnetic field. They precess around the direction of the magnetic field like this in this cone, and they will all be placed on the surface of the cone because they have a fixed angle. All of them have a fixed angle. They can't be anywhere. You have a fixed angle because the component of the magnetic moment along the z-axis is fixed. That cannot change. Therefore, if that component has to be the same, then the orientation has to be the same. So whether it is this orientation or this orientation, this angle is fixed. Okay, and there are a certain number of spins here, and there are a certain number of spins here. Where there will be more, there will be more here because this is lower in energy. Because we go back here, see this is lower in energy compared to this, and therefore there will be more spins here. There will be more spins in this orientation than here. What is the consequence of this? Now I take components of this on the z-axis, the x-axis, and the y-axis. Suppose these are nuclear magnetic moments, right? These are all nuclear magnets. I take components of that here, here, and also on the x-axis for both here as well as there. But you see what happens in the xy plane. This is my xy plane. If I take a circle here in the xy plane, for every one orientation, there's an opposite orientation. Okay? Because these are randomly spaced on the surface of the cone. For every one orientation, there's an opposite orientation here. And therefore, in the xy plane, there will be no net component. They will all cancel. They will all cancel. Whereas in the z-axis, since there are more spins here, there will be some net component here compared, and that is where I say here, this is the net magnetization, which is along the z-axis. So at equilibrium, if the system is at equilibrium, your magnetization is along the z-axis. There is nothing in the xy plane. This is said here, the equilibrium, there is no magnetization in the xy plane. It's transverse magnetization. What it means is there is no phase coherence amongst things. In other words, if this is not random, if this I have a cone here, okay, these are all random. If it is not random, what it means? It means there is a kind of a phase coherence. There is a relation between them. All of them have some kind of a relationship between them. They go together. If they go together, then there is no cancellation. Total cancellation will not happen. This is called as the phase coherence. The angle, what we have there is the phase coherence. If there is no transverse magnetization, then there is no phase coherence between the spins. If there is a transverse magnetization, it means there is a phase coherence created among the spins. This is a point to note. Remember this. We'll come back to this. So at equilibrium, there is no magnetization in the xy plane, and the net magnetization is only along the z-axis. We call this as mz or m0. And what does it depend upon? It depends upon the population difference between the two levels. Okay. So now here I've shown here. So this is the same. This is the precession here of spins on this orientation, spins on this orientation. Now I apply energy, apply radio frequency, which is along this axis. I apply another field. This is a small field, H1. This field is H0. Okay, this is the main field is H0 and or B0, whatever. And how much is this? This is in kilogauss. So if I take a spectrometer, which is like 750 megahertz, which is here, this is roughly how much? 17.6 Tesla. 17.6 Tesla. So each Tesla is 10 kilogauss. So that many kilogauss of the magnetic field is there. And how much is this? This is Gauss. This amplitude 2h1 cosine omega t, this is the oscillating RF frequency. This is the radio frequency. Electromagnetic radiation. Electromagnetic radiation is, you have the magnetic component of that, and that is 2h1 cosine omega t, and that h1 is the amplitude of that. How much is that amplitude? Is Gauss. Milligauss sometimes. Milligauss to Gauss. The extremely small field, which is applied along this, but it has a frequency dependent. It is an oscillating field. Okay, oscillating field is like this, 2h1 cosine omega t. Okay. Now, let's look at the oscillating field in this manner. Oscillating field is cosine omega t. Cosine omega t can be split into two portions like this. E to the I omega t plus e to the minus I omega t. What does this mean? E to the I omega t means which is going in the rotation in this direction. Minus I omega t means a rotation going in this direction. There are two, therefore, tiny magnetic fields, H1, whose amplitude is H1, and one of that goes in this direction, other one goes in this direction. Okay, so these are two opposite opposite rotations of this H1 field. Now, all the spins are going in a particular direction. Okay, this is called as the nuclear precision, as I told you. Suppose you sit on one of the, suppose you sit on the RF and look at this magnetic moments. Okay, which one do you look at? You look at one, the one which is sitting on the RF, which goes in the same sense as your nuclear spins. Then you will see that this is going at a slower speed. If you sit on the opposite one, it is going at a much faster speed. But you want to sit on that which is sitting, going in the same direction. And look at that. Look at the nuclear spin. So if your nuclear frequency matches the frequency of this RF, okay, cosine omega t, then it will appear stationary. That fellow, that nuclear spin will appear as stationary. What will then happen? If it is stationary, means it will have to interact with this H1 field. Then it will have to tilt away from there, because it has to come in the direction of this H1 field. It has to tilt away. See, if it tilts away means there is a transition which is happening from here to here. Because of that, there is a change in the population. There is energy absorption will happen, and therefore this is tilting away. What is the tilting away? Means it is energy that is getting absorbed. It's not normal equilibrium system anymore. Energy is getting absorbed. When that happens, there is a transition happening from this particular state to this particular state. So energy level diagram, if I want to see, if I supply the RF, which corresponds to this energy difference, I have a transition. Okay, absorption of energy. If I look at this picture, this is the classical picture. Classical picture, this is nuclear precession. I sit on one of those, which means I'm sitting on the rotating frame. That's called the rotating frame. Sit on this and look at this magnetic moment. If this frequency matches this frequency, which is going like this, then this appears stationary. Therefore, this will have to interact with this because it doesn't see any other field. It will interact with this. It will tilt away from that towards this field. Okay, and that is what is creating transverse magnetization. When you apply this, the energy is absorbed. It creates a transverse magnet. When you apply the RF, it will create a transverse magnetization. Creating transverse magnetization means what? Creates a phase coherence. It creates a phase. This is a very technical term, but I think I'm trying to get it in a very simplified manner. It creates a phase coherence among the various spins. Okay, so just remember that.
I have one question. So how
Yeah.
do you know that how much?
Yeah.
Whatever RF frequency you have to rotate?
Yes, that's one. This is the measuring part.
I see.
There's a measuring part. We'll come to that. Right there. How do you measure the signal? A priori, you do not know. A priori, you do not know what is the frequency of precession here and what RF frequency I should apply. So this is trial and error. So you scan. Just as you do in the optical spectroscopy, you scan through your frequency range and find out where your absorption signals are. You scan through the frequency. Either you scan the frequency, keeping the field constant, or you scan through the field, keeping the frequency constant. Either way you can do it. Okay? So scan through the field, keeping the frequency constant, because at some field it will match. Or is keep the field constant, scan the frequency so that at some frequency it will match, and there will be absorption of energy. That's called as the resonance condition. So therefore, we have nuclear magnetic resonance. Okay, so you have the nuclear term, magnetic moments. In a magnetic field, you apply radio frequency whose energy matches the precessional frequency, or it matches the energy difference between the two. Then you have absorption of energy, and that is your resonance. Okay, now how you should do that? When you sweep through this magnetic, conventionally, it was found more convenient to sweep the field. Why? In the early days, they were all electromagnets. Okay, electromagnets meaning you have a bar, iron bar, then you pass, there is a coil going around it, you pass current through that coil. Depending upon the amount of current you pass, you generate a magnetic field. It is easy to change the current. So therefore, you can easily change the magnetic field. So it was conveniently done at that time. It was convenient to do an electromagnet and therefore you have to scan through the field and how fast you should do it. Because you remember, when I change the field, the populations will change, right? the energy separation changes. Therefore, the populations will have to change. Now, if the system has to be in equilibrium all the time, you have to wait until the populations have reached the new equilibrium value. When you change the field, it has to reach the new equilibrium value. So you can't be doing it too fast. What is it that it depends upon? It depends upon a particular property known as the relaxation. Population changes have to follow the field changes, and this is determined by relaxation. In other words, once energy is absorbed, the system tends to come back to equilibrium. It loses the energy. We will see how it loses the energy, that we will see. It tends to lose energy and come back. Try to acquire the equilibrium again. Okay. And this is determined by a certain time constant known as T1. This is called as the spin lattice relaxation time. And this is the way it will approach the equilibrium value. Okay. N0 is the equilibrium value or the equilibrium value, whatever it has to reach. Okay. And this is the time. And you see, if time is t is infinity, time is equal to infinity, then of course this term goes to 0 and you have n is equal to n0. So typically, how much one should wait? If you want to hear, it should be typically of the order of 5 times of T1. If T is about 5 times of T1, then you are almost 99.9% you have come to that equilibrium value. So that much time one has to give, you have to sweep that slowly in order to reach the new equilibrium value and obtain the resonant signal. Follow the equilibrium function. Okay. All right. So that is so much for the NMR technique. Okay. Principle, the measurement, how you measure it, the conventional way of measurement. We'll come to the new way of measurement very soon. Now we look at the NMR. What is the information content in the NMR spectrum? What are the NMR parameters which are of significance for us? The first thing is chemical shift. Incidentally, I must tell you that chemical shift in the solution phase was discovered by an Indian. His name is S.S. Dharmati. He was the one who actually started the NMR group in TIFR in the 1950s. Okay, he worked with Felix Bloch. Homi Bhabha brought him to TIFR and he established the NMR group in TIFR. Okay, I will not go into the story because that will take time. Now, chemical shift. So this is the first NMR parameter which is of importance. What is it? That suppose you have a nucleus here. Every nucleus has an electron cloud around it, right? Every nucleus, whether it is proton or carbon or whatever you take, there is an electron cloud around it. Okay. Once you apply a magnetic field here, what it does, it induces currents in this electron cloud. Every time you apply, you must have heard of a battery, right? So, you know, you have certain kind of a torches. There is a small magnet inside in there. You shake it like this, you shake the battery, it starts lighting. Because what does it do? Well, there is a small magnet inside. You do the battery like this, torches, I'm saying the torches. You shake the torch like this, so this movement of the magnet inside generates an electric current. And that electric current lights up the bulb. So here also it is the same. You have a magnetic field applied. A magnetic field induces currents in these electrons and generates an electric current. And when the electric current is generated, it produces a field. This comes from electromagnetic theory. Okay? It produces a field, and this field generally opposes the externally applied magnetic field. And therefore, the field which is seen by the nucleus is not V naught itself, but it is somewhat reduced by a certain factor, 1 minus sigma I. Okay, if sigma I is positive, then this number is less than 1, it is less than 1. Then this number is, whole thing is less than 1. Therefore, Bi is less than B0. So therefore, it sees a field which is less than the B0. Now, this will depend upon what is the value of the sigma I. Okay, and that is the crucial thing. That depends on the chemical environment of the nucleus. The chemical environment of the nucleus determines what is this sigma I, and that is called as the screening constant, which depends on the environment. Accordingly, we define certain parameters called as the chemical shift. Okay, so suppose higher the delta implies higher Vi, implicating downfield shift and vice versa. So if the delta is higher, then of course you have on the spectra you have less screening, and that's why you have a higher delta. Okay. All right. So let us look at this particular example here. I have a molecule which is vinyl chloride here. There are 3 kinds of protons here: A, B, and C, and there is a chlorine group here. What is the chlorine group doing? The chlorine group has the tendency to withdraw electrons. Okay? It has a tendency to withdraw electrons. And of course, this effect will be relayed through the molecule. To what extent it will go, it will depend upon the structure of the molecule. Now it sees that this one will have the maximum effect on this one, then followed by this one, then followed by this one. Therefore, all these three ones will have different screening constant, the sigma I. Therefore, they will absorb energy at different frequencies. And you have three different frequencies here. The nu B has the highest energy separation. So the screening, we have pulled out the electrons maximally. Therefore, the electron density here is much less than followed by this and followed by this. Therefore, this is the highest frequency, followed by this and followed by this. So therefore, you have three different lines. And this is the chemical information. This is the chemical information, the structural information in the molecule. Right? This is the first parameter. Okay. Now, there are various factors which affect these electron densities, and that is electronegative substituent, which I already indicated to you. Then we also have so-called hybridization, paramagnetic groups, ring current defects, hydrogen bonds. We will not go into the details of all of those things, but I'm just listing here because there are many parameters which affect the electron density at the site of your nucleus. Anything that affects the field electron density or creates an additional field will affect your chemical shift. I'll show you one of those. Okay. On the basis of this, you see you have various kinds of chemical shifts there. For various groups, you have saturated things like the CH3 groups and things like that. They appear on this called chemical shift scale, 0 to 12 ppm. They appear at this here, or if the group is like this, they appear here and like this. So depending upon the nature of the group, what we have, the signals appear at different positions in that chemical shift scale. So we're always talking about the proton, okay? Proton here, everywhere we are talking about the proton. So where the proton absorbs energy, and that will be determined by the electronic environment around it. The same thing for the carbons here. The lower one is for the carbons. So here the carbon chemical shift range goes much larger. So this proton range goes up to 12 ppm there, and here it is going up to 200, 250 ppm. So this is a much wider range of chemical shifts there. And depending upon the nature of the group, functional group you have in your molecule, you have different chemical shifts. Okay. And these are very useful structural information. Okay. The chemists have used this extensively to characterize their molecular structures. Anytime a synthesis is made, you record an NMR spectrum. Whether your signals are coming according to the expectations as to where it should appear, that's what determines whether the structure is correct or not, your synthesis is correct or not. Okay, with regard to the aromatic rings, now there is a little bit more thing one has to see. If you have an aromatic ring or some kind of a double bond and things like that, here there is an electron cloud around above the ring and below the ring here. Okay, this is an aromatic ring here. There is an electron cloud here because this is coming from the pi electrons. The pi electrons are there up and down, the px and the pz. Okay, so those ones are here and they form a kind of a ring above and below. And the currents will flow through them. When the current flows through it, will also create a field. It will create a magnetic field, and these are the fluxes through the currents which are passing here, and these will tend to support or oppose the externally applied magnetic field. For example, if you're looking at a proton here, if this field is coming like this, what it's doing? See, it's going in this direction. So this is going in this direction. So it will add on to the field which is like this. So therefore, the field seen by this is higher than what is for the B0. And if the proton is somewhere here on the top, for example, here, and this coming in this direction, this is opposing the field, induced field is opposing here, the external applied magnetic field. So this will be on a different direction. So there are both shielding and de-shielding can happen in the case of the aromatic rings, depending upon where your proton is located with respect to the plane of the aromatic ring. Okay, so this is called the anisotropy in the chemical shifts. Okay, now, so that is so much for the chemical shift. The next parameter is the coupling constant. All the protons, as I said, are nuclear magnets, and they will also interact with each other. Just as the nuclear magnet interact with the external field, they will also interact with each other. And this interaction results in the kind of a splitting that instead of one line for each of these two protons, we get two lines here. Because of one coupling here, this coupling from here to here results in a splitting of these lines. This is called as the coupling constant, and this will be the same in both places. Take for example, if there are more protons which are coupled, there will be more multiplicity here. For this CH3 group, for example, there is more multiplicity because it is coupled with the proto-protons here, and these proto-protons are coupled to the 3 protons here and to the OH group here. Therefore, there is a fine structure in each of these lines, and that is extremely useful information from the point of view of structure determination. Multiplicity will determine what sort of a neighbor you have in your molecule. Okay, so this is the one. This is 1:3:3:1 multiplet. This will immediately tell you that is adjacent to a group which contains CH3. So 3 couplings are there. So therefore you have this sort of a pattern. Okay. And the third parameter is the relaxation time. I already mentioned to you about the relaxation, T1 relaxation, which is called the spin lattice relaxation. And that is the spin lattice relaxation affects the populations of the states. Its system comes back to equilibrium because of the relaxation process. Okay. And then there is another relaxation time, which is called the transverse relaxation time. I remember I told you when I apply an RF, I create a phase coherence. There is a magnetization created in the transverse plane, but this cannot remain there forever. Okay, this phase coherence will slowly destroy itself. When the phase coherence will destroy, there is a transverse magnetization will destroy, and that goes with a different characteristic time, and that is called as the spin-spin relaxation time. So you have 2 relaxation times. One is for the longitudinal magnetization, that is the Z magnetization. The other one is for the transverse magnetization, and this is called the T2, and this is called as the T1. So 2 different relaxation times are there. Okay. Now the sensitivity in NMR is proportional to the strength of the magnetic field. You see the population here, depending upon the field, as I said, 100 megahertz energy separation is this much, 200 is this much, 400 is this much. And therefore, accordingly, the population differences also will be different. Okay. Therefore, depending upon that, your sensitivity will be different. If the population difference is more, there will be more number of spins which will be absorbing energy. Therefore, the signal will be higher. So therefore, you need to have more separation. Therefore, what you do, you go to higher fields. As you go to higher and higher fields, your population differences will increase. So therefore, you will have a higher and higher signal. Sensitivity will be higher. And that is therefore a motivation for creating strong magnetic fields, higher magnetic fields. In the early days, it used to be like 30 to 100 megahertz. When it was first started in TIFR, it was 60 megahertz, and it was the electromagnet. And now we have 2020, 1.2 gigahertz. 1.2 gigahertz magnetic field is available today. Okay, this is corresponding. And this was just few years ago. There are not too many instruments of this type. Okay, you see the cost wise is prohibitively expensive. Okay, now a 900 megahertz which is listed here, this will cost you about 40 crores. 55 crores. Recently got the quotation, 55 crores. Okay. Now, how much this will be? 1.2 gigahertz. Is it not possible for us to? We cannot afford it. Extremely expensive. But the technology is also very different. And now the electromagnets are gone. You have what are called the superconducting magnets. The superconducting magnets, you have a magnet, once it is created, it stays there forever. You don't need to pass current continuously all the time. So electromagnet, you can switch it off. Here you cannot switch it off. Once you charge it, the current keeps going there and forever. And you have to keep filling helium. You have to keep filling helium to keep the material in the superconducting state. So therefore, it is the persistent current, therefore the persistent field. And that also has reduced the size of the spectrometers, the size of the magnets, and that is enormously great technological development, but the cost-wise, it is extremely prohibitive. And then advances in computer technology have also contributed to all of this. And you can see here, this is becoming more and more important. As you go into artificial intelligence and deep learning, this becomes even more important. Extensively dependent on the computer power. Okay, the searching tool. Okay, now, so far as the general principles are covered with regard to the observation. Now I come to the new method of detection. So far we talked about the slope of flow passage. You pass through slowly and then measuring. But however, this is a slow process. If the slow process means actually you cannot do it for too long. So you need to have things which are faster. And this was the first revolution in NMR, the Fourier transform. And this was done by Richard Ernst in 1966. So what it does is that if you apply a RF, instead of applying it for a long time continuously, you apply it for a short time. Okay. In the earlier case, we say we apply for RF, apply it continuously. Then you have signal. When they were matching it, there is a signal. Here you don't do it. You apply it for a short period. Apply for a short period, something like about 10 microseconds. Of course, the computers are required here, right? How do you control this 10 microsecond or 5.5 microseconds and things like that? You need to have computer control. So when you apply the RF for a short time, what it does is it actually excites all the spins in your system. All the spins are excited at the same time. And we will see that. And another thing that it does is that it rotates this magnetization out of the z-axis. Okay, I told you the RF application itself creates a transverse magnetization, and this pulse is not different. It's applied for a short time or a long time, it doesn't matter. It does create a transverse magnetization. Now, if you apply it for a short time, it will rotate the magnetization to a certain angle, through a certain angle. Okay, and that angle is given by what is called by this equation here is proportional to the gamma h1 times tau. Tau is the time for which you apply, and this is h1 is the amplitude of the RF, and this is the angle which it covers. Okay, now if this angle is 90 degree, then the magnetization rotates from the z-axis to the transverse plane, to the x-axis. Now this is the entire magnetization, remember, okay? Not only one spin magnetization, the entire magnetization rotates into the xy plane. Okay, that's called as a pulse. The pulse rotates the magnetization into the transverse plane. Now, yeah, this is in the rotating frame. Rotation of magnetization into the wire. Okay, this is indicated by here. If you apply 90 degree pulse, this magnetization comes over to this. By 180 degree pulse, that means if this angle is equal to 180 degree, magnetization comes here. This is called as the inversion. If you apply the next one, apply a 270 degree, then it comes here. Okay, so you can place it wherever you want, depending on how much rotation you want. You will give by adjusting this value of tau. This tau, you can put the magnetization in different positions. Okay, you have created a phase coherence now among the various spins as a result of this. Now, after this, what happens? After they remove the pulse, RF is removed. What will happen to it? It has to go back. It has to go back. It has to lose the phase coherence. So therefore, the T2 relaxation will come into the picture once. Then it also has to go back. The populations will have to equilibrate. Then it has to, the T1 relaxation will also come into the picture. So therefore, system will go rotate here and eventually slowly recover and come back to the z-axis. So this is the process of relaxation. But when it is doing here, it will actually go through this plane rotating, right? Because the spins are precessing. The spins will have to precess. That is the interaction. And when they are precessing here in the transverse plane, this is a rotating magnetization. The rotating magnetization will produce current. As I said, the same thing, the opposite of which, what I said, a field which is state produces current. Here also the rotating magnetization produces a current. And that current is the voltage inside this detector here. So therefore, this is your signal. The rotating magnetization here induces a voltage in this detector, and that is your signal. Okay. Now, if there are many frequencies here, if there are many frequencies in this one, because as I said, all the spins, they have individually, they have different frequencies. Therefore, when they go back here, they will go with their characteristic frequencies. Omega 1, omega 2, omega 3, omega 4, omega 5, omega 6. You have 100 frequencies. All of these 100 ones will go with their characteristic frequencies. And they all will induce current here, and their voltages will be different. So therefore, the signal that will come here will be a kind of a sum of the signals from all these rotations. Okay, what does that mean? And that is what is called as the Fourier transform. Okay, the Fourier transform is the summation of the various components. Okay, you have one frequency going around, another one going around, the third one going around. All of them are inducing a signal voltage here. So you have got the sum of all of those. And the sum of that is basically the Fourier transform, all the frequencies which are present here. Therefore, if you do a Fourier analysis, you will get to know what are the frequencies which are present inside there. And that is the principle of Fourier transform NMR. Okay, now what we have got here, what we have achieved, you applied a pulse for 10 microseconds, and your detection is for a few hundred milliseconds. For the transverse magnetization disappears in few hundred milliseconds. The T2 relaxation is of that type. Therefore, you collected the signal in 200 milliseconds. You collected signals from all your frequencies. In the slow passage, you would need to do it for 10-15 minutes. Scan through it one by one if you want to do, then an extremely slow process. Here you have got it in few hundred milliseconds. The extremely significant step. And that's why I say it is a revolution. And see, that is the principle of Fourier transform NMR. You have the signal which comes as a function of time in the detector, and the Fourier analyze it, you get the frequency domain spectrum, you have the analysis done. Okay. So that is what is indicated in this slide. So you have, this is the so-called FID, this is the signal which contains contributions from all the frequencies which are present. So if you have one frequency present here, you will have one line which is present here. Notice this frequency, the signal decays with the time, and that is because of the phase coherence which is present that decays with the time. The phase coherence decays, and that's why this transverse magnetization decays here, and you have the signal which is, and this will have a line width which is related to this transverse relaxation time. Okay. If you have two signals, the superposition FT will produce you two signals. Okay. If you have more, 3-4 lines, your FID will start looking like this. Your two signals, FID looks like this. So you see, there is one frequency, the separation between these two is another frequency. Separation between from here to here, here to here, here to the peaks is the same. When there are only two frequencies, you can identify that. When there are many frequencies, you cannot do it. Here you cannot do it. If you have 4 lines, see the FID looks like this. Okay, and the signal is called FID because it is called free induction decay. The rotating magnetization induces the voltage in your detector, and therefore it is called as a induction, free induction. And if you have many lines, then of course you have the FID which looks like this. Now the only way to analyze this is to take a Fourier transform of this one, and you get the NMR spectrum. All right, so this is what is done by Richard Ernst, and this was published in Reviews of Scientific Instruments. Incidentally, I must tell you one story here. When this paper was submitted to Journal of Chemical Physics, it was rejected. It is submitted to how many places, I don't know, at least 3 places he submitted, it was rejected. So finally, it got accepted because you see, this is the CW spectrum. It's a slow passage spectrum. The slow passage spectrum of this molecule looks like this, recorded in 500 seconds. One scanning through this in 500 seconds, it produced a signal which is looking like this. And the same molecule in the same time, 500 seconds, produced a spectrum like this. Nobody believed it. It's a humbug. You have something which is absolutely dirty things in your sample, and you are getting some things like that. Nobody accepted it. But of course, ultimately, the truth prevailed, and this was accepted in Reviews of Scientific Instruments. Actually, I should also tell you how this Fourier transform idea came into Richard Ernst. He was working with radars. You know, he in the Varian company. He went after his PhD. He went to do a postdoc in the radar company. Varian. They were making radars. They were dealing with radio frequencies, and that is where it struck to him that I should use radio frequencies for NMR, because he did PhD in NMR, and he used the radio frequency. They're dealing with it day by day. Every day they're doing it radio. So therefore, and that is where he got the idea. So Ernst and Anderson. The Anderson was got there in Varian instruments. Okay, so breakthroughs by FTNMR. First is time gain, sensitivity, therefore the low concentration of the samples can be used. The concentrations are often limited by solubility, availability, viscosity changes at high temperature, etc. Nuclei with a low natural abundance such as carbon 13, hydrogen 15 can be studied. Signal averaging, which is a must in these cases, can be easily performed. Why? What it means here that you keep adding your signals. Keep signal averaging means you keep adding your signals, and you do the Fourier transform once at the end. Okay, the previous experiment, there are 500 scans were added, and the Fourier transform was done at the end. Therefore, signal averaging was easy to do, and then you have, due to enhanced speed of data acquisition, short-lived species, half-life seconds only, can readily be studied. Okay, can you do this by any other technique? short-lived speech, which has only lifetime of about a few seconds or a few minutes. We cannot study that mainly. So get the details of that. So dynamic processes can be investigated and data can be collected as a function of time. Okay. These have opened up enormous applications of NMR in various areas of chemistry and biology. Okay. Now there is one particular thing which is, okay, now here is certain examples here. The C13 NMR spectrum at natural level, this was unthinkable in the early days. Before Fourier transform NMR, you need to produce samples of 1 molar size, concentration of 1 molar. Okay, then only you can get a C13 signal at natural abundance. Okay, here at natural abundance, the signal is recorded so comfortably and conveniently. You see the fine structure here, and you can also remove the couplings there, and then there is the signal here, singlets, and you can count the number of signals there, how many are present in your molecule. And of course, the intensity of this is also dependent on how many carbons of that type are present there. Here there are 2 carbons, here there are 4 carbons of the same chemical shift, and therefore the intensity is 4 times compared to this. And therefore, you can record the spectra of carbon-13 at natural abundance, and this becomes an extremely useful tool for the organic chemist. How many carbons are there in your spectrum, in your molecule? Record a carbon-13 spectrum, decoupled spectrum, and which are its neighbors? Record a coupled carbon-13 spectrum, proton-coupled carbon-13 spectrum. Then you will see what are the multiplet structures. And that is how this becomes extremely important technique, and all this became possible because of Fourier transform NMR. There is one other important consequence of Fourier transform NMR, and that is the so-called segmentation of time axis, and that is excitation and detection of separated in time. See here, you excite your system by the RF. You apply a pulse. For a short time, 10 microseconds. After that, you don't do anything. You simply collect the signal. Therefore, detection and excitation are separated in time. That gives an idea that, okay, there is a time here. And now, depending upon whether you collect the signal right from this time 0 or you collect from here, it is the same. You are not losing information because from everywhere from here to here, it is the superposition of all the signals. So no frequency information is lost. Of course, we may have phase distortions, etc., but frequency information is not lost. Whether you collect from here or from here, all the frequencies are present. You do Fourier transformation. Therefore, what I can do is, this generates an idea. Well, I give a gap here. I give a gap after the excitation. I give a gap. I do some perturbation. I do some manipulation. And afterward, I collect the signal. All my signals are there, but I have the possibility of manipulating the spin system in the way I want. Okay, that is what led to multidimensional NMR, 2D NMR, spin echo, and so many things. Okay, that is one illustration of that is this, the spin echo. Spin echo is you first excite the system here, and then you for a time period tau, then you apply 180-degree pulse here. I already showed you what is a 180 pulse, 190-degree pulse. Then you apply wait for the same time tau, then you will see the signal comes back here to the same what it was at the beginning at this point. That's why this is called as the echo. The signal which is coming here, the FID is coming down like this, and you apply a 180-degree pulse, you reverse it, it's called the time reversal, you reverse the thing, and then it starts going up again. Starts going up, and when it comes here, it is the same signal which is present at this point. I will explain this to you with a vector diagram. In the next slide, how does this happen? For example, here, 2 uncoupled spins. Okay, doesn't matter, can focus on one. So you have these 2 uncoupled spins which are present here with the cyan and the red arrows. Z magnetization is here, the 2 spins. You apply 90x pulse, the 2 components, the 2 spins have come here. Okay. During the next time tau, what happens? They will start processing in the transverse plane. They will start going around with the characteristic frequencies, B here and A here, because they have different frequencies. They will go to different frequencies. Now you apply 180-degree X pulse. That means these ones will come over onto this side. The cyan one will come here, and the red one will come here. So this is going down and coming up, start falling down on this side. And now during the next time period tau, what happens? This will move by this much angle. This will move by this much angle, because that is what they did here. From here to here, this B move with a larger angle than A. So it will the same thing will happen here. This blue will move here, and the orange will also move here. Therefore, what happens at this point? They all have come back here. At point 5, they have come back to this same position. Nothing is lost. Therefore, it is called as the echo. Echo means what? You shout, your own voice comes back, gets reflected and comes back. This 180-degree pulse is basically doing a reflection. It's doing a reflection of the magnetization. Okay, so in front of the hill you shout, your own voice comes back, right? Why? It gets reflected from the hill and comes back to you, and that is the echo. So here this echo amplitude is the same. Now notice here, no matter whether you have the cyan on the red, which have different frequencies, both will come back here. So the frequency doesn't matter. No matter what the frequencies are, I consider two. Suppose there are 10 or 15, all of them will come back. All of them will come to the same point. Therefore, chemical shifts are refocused. The spin echo refocuses the chemical shifts. This process of 90, 180 tau, 90 tau, 180 tau, refocuses the chemical shift. That is called as the spin echo. Spin echo is an extremely important concept. This was done by Erwin Hahn. In fact, he should have got the Nobel Prize also. Unfortunately, he missed it. That is, whatever reason, it is the same thing. Because this is a component of various NMR experiments. Two-dimensional, three-dimensional, four-dimensional, everywhere, this spin echo is an extremely important concept. This is okay. So therefore, the chemical shifts are refocused. There is, with regard to the coupled spins, I will not go into the calculation of this, but I only want to show you that in this case, the two things do not refocus. The two components, because the A transition, A spin will have two lines. In the earlier case, A had one line, other one has one line. If you have a coupled spin, A will have two lines, this also will have two lines, orange also will have two lines. Now here, this will not refocus. The coupling, when there is a coupling, they will start fanning out even more than at the end of the echo. Therefore, we will simply say the angle between the two lines A1 and A2 at the time of echo is given by this 4 by J times tau. J is the coupling constant. So therefore, you see when the tau is equal to 1 by 4J, what will be the angle? It will be pi. Okay, so they will be oriented opposite to each other. And that is an extremely important concept which is used for various manipulations. Okay, one last point which I will show, this completes the introductions of the NMR concepts. And that is the so-called nuclear over Hosur effect. This was also done in the 1970s by over Hosur. Idea here is simple, that we know that the nuclear spins interact with each other. If I perturb one spin, what happens to the other spin? Does it take away the perturbation? Does it take the perturbation from one to the other? Indeed, it does. Because there is a coupling between them. They interact with coupling. There are two possibilities of coupling. One is the so-called spin coupling, which I showed you. The other mechanism of coupling is direct dipole-dipole magnetic coupling. Because these are magnetic dipoles, nuclear magnets. The nuclear magnets interact with each other. Okay, so that dipole-dipole interaction which will be there, that relays the perturbation from one spin to another spin. So therefore, I have a spectrum here of a particular molecule, which is a protein here. Now, if I perturb one of these spins here, I perturb this line, this corresponds to one particular spin in the protein. So I do an experiment, I perturb it, that means I hit the RF corresponding to that, I perturb it. Then I do another experiment without perturbation, I don't perturb it. Then I take a difference. When I take a difference, what do I get? This is the difference spectrum. Of course, when there is a perturbation, no perturbation, this will have the maximum intensity. And you see intensity is at other places also. Why? Otherwise, if it were all the same, it should be zero. But there are intensities here as well. That means this fellow is interacting with these protons. This is the NOE. This is called the nuclear over Hosur effect. So you perturb one nucleus, it transmits this perturbation to another spin, which is nearby, because this is through the dipole-dipole interaction. Dipole-dipole interaction goes by 1 to the 6th power, inverse 1 to the 6th power. So therefore, this is goes to a very short distance, not more than 5 angstroms. So typically, if you have such a kind of a short distance possible with regard to the perturbed spin, you can figure out what is this proton. This becomes an extremely useful technique in organic chemistry and in biology as well, in structural biology as well. But this is a structural feature. Which protons are close by in space? This is an extremely useful input. Okay, and therefore NOE has become an extremely important concept in NMR. Okay, and you see the kind of NOE, what sort of NOEs enhancements you will get. This will vary from proton to proton, and in the molecule to molecule, and that depends upon the molecular motions inside the solution. Molecules are tumbling around, so depending upon the rate at which they are tumbling, you will have different kinds of NOEs, and you have small molecule, big molecules. What are these? 10 to the power tau c. Okay, now here is a correlation time. That means correlation time means it is the rate at which the molecule tumbles, how fast it tumbles. Okay, nanosecond time scale, microsecond time scale, or picosecond time scales. So depending upon the time scales of the motions of the molecules, if the molecule is big, it is very sluggish. It cannot move too fast. If it is very small, very rapid movement. Okay, and so here these are molecules which are very small. Here are molecules which are very big. And you see the NOEs can have positive or negative signal depending upon whether it is a small molecule or a big molecule. But when you are talking about proteins, we are mostly talking in this domain. Okay, and this becomes an extremely useful technique for structural biology. Okay, I think I will stop here at this point. So this is for the in future, and this is the thing which was taken picture taken in TIFR. Here you have Kurt Wittrich and Richard Ernst, and this is Ernst's wife. They had come for a conference at TIFR. It was taken in TIFR. These were the two pioneers of generating structural biology, Fourier transform, multi-dimensional lens, all of those things. Okay, and I think I will stop here unless you have any clarifications to see. And you can tell me if it is going at the right speed and the important messages are given. Of course, the details, mathematics is not required. It's not required to go through. Essential things I've already given to you. So the next lectures, as I mentioned to you, we'll talk about the protein structure determination using these principles. And after that, we will go into the dynamics part. Dynamics, as I said, dynamics is intrinsic to NMR, intrinsic to NMR. So, and that will be the third lecture. We will go in that process. So if you have any suggestions, you can tell me so that I can modify my lectures. Sorry? Multiplex? So multiplex occurs because of the spin coupling. Okay. Environment is dependent on the chemical shift. Because of the chemical shift, there are different environments. Okay. The coupling constant will also depend on the electron density, intervening electron density. Okay. Which is the larger coupling, which is the smaller coupling, will also depend upon the electron density in between the bonds. Okay. The trans coupling is higher than a cis coupling. Because that is how the electron transfer happens within the structure of the bond. So this can be calculated. So there are quantum mechanical methods to calculate the coupling constant between these two. You have one nucleus, another nucleus, there's a magnetic dipole, you have electrons in the middle, then you have the relay through the electrons, so that calculations are possible, but empirically, you have the trans thing is the larger coupling than the cis. And geminal couplings are usually negative. Geminal couplings are negative, vicinal couplings are positive, and single bond couplings are positive. Okay, geminal coupling is 2-bond coupling, no? Okay, and vicinal coupling is 3-bond couplings. These are positive. And geminal couplings are of the order of 14 to 17 hertz. They are negative. CH2 group. And vicinal couplings can range from 3 to 10 hertz. 1-bond couplings can vary from depend upon the system. Proton coupling is very large. Of course, you don't see proton coupling mostly. You see carbon 13 proton coupling, nitrogen proton coupling. Nitrogen proton coupling is of the order of 90 to 100 hertz. Proton to carbon coupling is about 140 to 160 hertz. Okay, so those ones are dependent on the electron density there.
we then see a particular element other than carbon on each and every element.
In the oil, see, wherever there is a magnetic moment, you have NMR positive. And if spin is 0, I is equal to 0, then you will not see this. Carbon 12 is 0, therefore you don't see the carbon 12 factor. Okay, carbon 13, nitrogen 15, nitrogen 14, all of this. So if it is a spin half, that is what mostly important for biology and chemistry. In materials chemistry, of course, other things also become important, like spin 1. Spin 1 becomes also important, but when spin 1 it becomes a photopolar nucleus. Photopolar nucleus has more complications. Lines are broader there, photopolar moment acts, and they provide the relaxation mechanism. So that's generally critical. So we avoid that in biology. That's why you go to nitrogen 15. See, the proteins we generally produce now with nitrogen 15 label and carbon 13 label. Otherwise, you can't do this multi-dimensional experiments. And this for this labeling, we need to do biology. Okay, proteins have to be expressed inside the cells, which grow in nitrogen 15 source or carbon 13 source. So they incorporate that into a protein, so you get conformally enriched carbon 13 or nitrogen 15 or doubly labeled proteins. So it's an integration. So biology is getting integrated into our foods. Yes.
What is speed? Are you sure that this 90 plus after that, tau afterwards 180?
Yeah.
So this tau are same or different?
Yeah, same. Yes, same. The two taus are the same. 90 tau, 180 tau. That's the spin echo sequence. Then only it will come back to the same position.
No further
No
question.
further questions?
Let's
Okay.
thank Professor Hosur for lecture. And next lecture will be here on Thursday at 4:30. Right. The 3 lectures are going to be here. 2 lectures, I think, on 22nd and 29th probably are going to be in LT 002. Okay. On Thursday. Thank you.
Right? He's actually one of